那我们选 B。好记得。手机放，我好像是手机放，真的吗？因为你去完美，你就放。我等一下介绍的时候才看得到各位的名字。全名吗？
这讲了，他小时候本来不爱看书，看书嘛，看书，然后他就爱看书。起名字叫师兄。
My name is Luo Fangyu from National Taiwan University, and I'm the chair of this physics fight. So at the beginning, I would first welcome. I would like to welcome all three teams, and now we have already decided the team A, B, C. So the team A is Beijing Normal University. The team B is Nankai University, and team C is Zhongxing University. So first, I would like each team to introduce the team member. So let's start from team A.
Good morning, everyone. I'm Ding Chuchong, a team member, and this is our captain, Zhang Yibing, and this is Shi Kai, Duan Jingzi, and Lan Jia Wenjing. Thank you, everyone.
Good morning, everyone. I'm Zhang Xunjian from Nankai University, and this is Wang Keyu. This is Xin Huiyan. This is Tang Yugan. Thank you very much.
Good morning, everyone. I'm Zheng Qingwen from Zhongxing University, and this is Shi Benren, and Zhang Chuanyu, Qiu Guofeng, and Luo Zixuan. Thank you very much.
Now, I would like to introduce our jury member. So, besides me, there is Professor Xu Mingsheng from Military Academy. So, and there's Professor Gao Sijie from Beijing Normal University. There's Professor Liu Wenbiao from Beijing Normal University. Let me say, in 1 minute, after 1 minute, we will start our physics fight, and then we will have take the report of Team A, and then Team B, and then Team C. So each have 10 minutes. Are you ready?
Yes.
Well, then let's start.
Okay. Good morning, everyone. It's an honor to be here to talk about the question Single Lens Telescope. I'm Ding Shicheng. Thank you, everyone. And this is my content. Includes problem, theory, experiment, application, and conclusion. First, let's review our problem. A telescope can be built using a single lens, provided that a small aperture is used instead of an eyepiece. How do the parameters of the lens and the hole influence the image? Examples are magnification, sharpness, and brightness. And the keywords are very obvious: the lens, the hole, which is the aperture, and the image factors like magnification, sharpness, and brightness. And all we have to do is to replace the eyepiece, which is on the left of the left telescope, with an aperture, and this is our telescope. And first, let's see some of our pre-experiments. We can see that the image factors like brightness, magnification, and sharpness varies quite a lot under different conditions. So that leads to our question: how does the parameter of the telescope affect these factors? And this is my theory and experiment, concluding magnification, brightness, sharpness, and other important image quality factors. The first is angular magnification. When we talk about telescope magnification, usually it refers to angular magnification, because angular magnification demonstrates the size of the image we see with our eyes. And for an object that is very, very far away from us, we can say that the object distance, we can take it as infinity away. So the image must be at the focal plane. And there are two cases. When the aperture is behind the image, which is here, the L is the distance between the lens and the aperture. So L is larger than F prime. We can get, using some simple geometry, which I'm not going to go into detail today, the magnification is here. And it's positive, so it's a positive image. And another thing is when the aperture is in front of the image, which is L is smaller than F prime, so we can still get the image, get the magnification. It has the same form with the other one. So we can see that the relative position of the aperture and the image doesn't change the magnification. In this case, it's negative, so it's a negative image. But all I have just said was just theoretically, because in our experiment, we can never get an object infinity away from us. That's why we need to correct our magnification with limited object distance here. And this is the angle of the object we see using our naked eye, and this is the angle of the object we see using telescope. And the ratio of the tangent of these two is our magnification, which is here. You can see it's pretty complicated, but if we let the S, which is the object distance, goes to infinity, we can still get the original magnification here. And then it's our experiment. This is the theoretical magnifications we predicted and calculated, and this is the experimental magnification we observed in our experiment. And K is the coefficient. You can see it's approximately equals to 1, which means our theory can predict this magnification pretty well, pretty perfectly. And let's move on to brightness. Okay, there are many quantities can demonstrate brightness. I mean, like light intensity can do that. But the problem is our eyes have different sensitivity to different wavelengths of light. But intensity can demonstrate that. Another quantity is luminance. And when we the luminance considers the sensitivity of our eyes, but the problem is it's obvious that we can use our telescope to see the moon, but it's not recommended to use it to see the sun because it's too bright. So if we want to demonstrate the brightness of the telescope, to demonstrate its performance, it should be irrelevant with the object, irrelevant with the luminance of the object. That's why we introduced this one, the subjective luminance, which is the ratio of the luminance of the object we see with our telescope over the luminance we see with our naked eye. That is irrelevant of the object. And we all know that the luminance here is proportional to luminous flux over A. Phi is the luminous flux and A is the size of the image. And so our subjective luminance should be here is the ratio of the luminance of the telescope over the luminance of the naked eye. And this is what we got. M is the angular magnification. DE here is the diameter of our pupil in our eyes. And dt is a little bit complicated here. It's the minimum one among the diameter of the pupil, the aperture, and the lens. It is easy to understand because if our pupil remains unchanged, the total light that can go into our eyes is constant. So if the aperture is larger than our pupil, no more light could go into our eyes, so the brightness won't change. And here's some of our experiments about dt and about magnifications, which fits perfectly. And then let's talk about depth of field. First, let's see a video. When we move the object towards the telescope, we can see that the image is getting fuzzier and fuzzier. But within a certain range, we can call it a clear image. And that range is called the depth of field, DOF. And our theory is that the condition for clear image is when theta is smaller than 60 degrees. Theta is the visual angle of the image to our eyes here. And with some calculation, this is the depth of field we get, DOF. It's pretty complicated. And our experiments show that when within the DOF, it's pretty clear. And beyond the DOF, it's pretty fuzzy. But we are using our feeling to decide which is clear and which is not. That is too subjective. That's why we need to introduce another one, sharpness. First, let's see some of the gray level image. We can see that this image has the sharpest. This is the sharpest image of them all, and here is their distribution of the gray level. So that leads us to think that sharpness means the sharp of edge, which inspire us to use gradient to define sharpness. And this is our definition for sharpness. It's the average length of the gradient of gray level on the edge of the image. And here's my methods to calculate sharpness. First, we convert our image to a gray level image. And then we detect the edge of the image and we calculate the gradient here. And we calculate the average gradient of the edge. And that is our sharpness. And here's some of our calculation. We can see the first one is has the highest sharpness, and the third one has the least sharpness. We can also tell that from the image. And this is a gray level distribution that can tell us the same thing. But another thing is we are taking photos to get the photo of the image and convert to gray level. So there are some of the errors that cannot be taken out. That's why we need to find a steady and more steady quantity. So how to qualify image quality better, and that's where we should introduce the image quality assessment and the modulation transfer function, MTF, which is widely used in optical engineering to demonstrate the quality of the image. And this is the definition of our quality, quantified quality. And after calculation, we get the quality of our telescope. The image of our telescope is here. And we can calculate different quality for different images. This has the highest quality, and this has the lowest quality. So now we can compare each other, compare the quality of each photo with each image. And we can have some interesting conclusions, like the optimum aperture. So for every telescope, there exists optimum aperture, or we can say the best aperture size, to give us the best image or the highest quality of image. And so to do that with our quantified quality, you can use this formula to this condition to decide which has the highest quality, and this is what we got. The size of the aperture is a function of L. L is the distance between the lens and the aperture. And for one experiment, for L equals 0.18 meters, the aperture size is, the perfect aperture size is 0.55 millimeters. And this is our optimum size of the image. And it's sharp and light. So if it's smaller than, if the size is a little bit smaller, 0.5, it is sharp. You can see from here, it's pretty sharp, but it's too dark. And if it's a little bit larger than the optimum size, 0.6 millimeters, it's pretty bright. We can see from here, but it's too fuzzy. So the sharpness is too low. That's why we can, for some certain degree, we can tell that this is the optimum size of the sharpness. And here's my conclusion. First, we observe some optical characters like the angular magnification and brightness. Then we have the image quality like depth of field and sharpness, which inspire us to find a quantified quality That's why we introduced the quality assessment and the modulation transfer function. And we calculated the best optimum aperture size, which is here. And here's my reference. Thank you, everyone.
Thank you for the report. Now it's Team B's time for the report.
加油！
So please go ahead.
Hello everyone. I'm Zhang Xinjian from Nankai University. I'd like to give you a report of problem number 3 in Single Lens Telescope. Firstly, let's review the problem. This problem brings us two tasks that, firstly, to build a telescope with a single lens and a small aperture, and secondly, to investigate how the relevant parameters influence the image. And this is our content. In the first part, we have built a single lens telescope just like this. On the left side of the telescope, we set a convex lens and an adjustable lens cone and link it to a small aperture. This is the real photos of our experimental setting. And our following discussion will go around the 3 particles, that is the lens, the cone, and the aperture. This is, we chose a symbolic tower in Tianjin as our fast sample, and this is the original image directly taken by camera. And after we add a pinhole, we found that this image is darker, but it is more clearer. And with only a lens, we could find it's really blurry. Only with both of them that it could correctly image. So we know that lens can magnify the object, and secondly, the pinhole can make the image more clearer. And we also found that for 2 values of the cone lens, it could image that is when the length of the cone is shorter than f, we could find that it makes an erected image, and when the length is longer than f, we found that it makes an inverted image. And these 3 particles have 3 parameters we really interested in. That is the focal length of the lens, and the pinhole diameter, and the length of the cone. The 3 parameters makes an image on our retina. And here we use a camera to receive the image to replace our retina. And we will analyze the 3 parameters, that is the magnification, the sharpness, and the brightness. We will study it in order, and firstly, let's see the magnification. Magnification could be defined as the angle of your solid eyes to visual and the angle of the settings, and could be written like this. We could say that M is only correlates with the focal length and the cone length. We built a simple experimental setup which is similar to our above setting, and just in the laboratory, and we can find that this is our objects, and we found that for different f's, when the f increases, the magnifications on the different curves decreases, but on the same curve, when we increase the L, we find that the magnification firstly increases, then inversely decreases like this. It is a hyperbola, just like our theory predicted. And we can see that the left curve means makes an upside image, and the right part is the headstand image. And these are the real pictures. We could see that it is bigger and bigger and smaller and smaller. Okay. Here comes the sharpness. Sharpness could be defined as the gradient of grade level G. We could see that the upper grade level is higher and the grade level in the bottom is lower. So in the picture, we could see the upper side is clear and the under one is blurred. So just like this. The gradient G increases means the sharpness increases and the image becomes clearer. Okay, in our experiment, we could define the gradient G, simplify the gradient G as delta G divided by delta X. And delta X is finally limited by the the radius of area disk, like this. And so the gradient G could be written as this. Then we may ask, firstly, how the magnification M influences gradient G, and how the pinhole diameter influences the gradient G. Influencing the gradient G has two ways, that is, influence the delta G and influence R. Firstly, let's see how the magnification M influences delta G. We did many experiments in changing M in a wide range, and only to find that there is no relationship between M and delta G. However, when M decreases, the solid angle of the sample decreases, then R decreases. Therefore, the gradient G will increase. And we did experiments to check. We use the middle line of the image as our sample, and this is given by MATLAB, and we found that the maximum gradient as our data here is 5.5, and we draw this picture. We could find that the gradient G decreases as the absolute M increases. Then let's study how pinhole diameter D influences gradient G. Firstly, we just simply change the pinhole diameter, and to find that when the pinhole diameter increases, the view field is brighter and brighter. Of course, yeah. And for the area disk radius, we made a simple simulation, and we could find that when D is so small, the diffraction is great, and the dot is so big, and when it is the diameter decreases, we could find the peak is sharper, and when it finally increases, we find the peak is not so sharper because the light could easily pass the pinhole. So we could find diameter increases and the radius firstly decreases, then increases. Then we could simply get gradient G with by the R divided the delta G, like this. This is use the two data to get this, and the red dots as our experiment dots. We could see when D increases, gradient G firstly increases, then decreases. Last one is brightness. Brightness is the illuminance of image on the retina, and after simple calculation, we could find that the illuminance of image on the retina is proportional to D squared. Then we just change this D to find that the view field is brighter and brighter. Is of course, yeah. And the illuminance of image on, the experiment data could be fit as linear fitted like this, and we could find that the result is consistent with theory. That is, the illuminance is really proportional to D squared. Here comes our conclusion. We studied three parameters, and the lens focal length and the core length influence M jointly, and all these three parameters influences the sharpness gradient G, and only the grid pinhole diameter influences the illuminance. And we have self-built a telescope and studied its parameters. And we found that its observation range is 10 to 1,000 meters, and its ideal angular resolution is 10 to 12 times. This is our references. And thank you.
Thank you for the report. Now it's time for Team C to report their results.
Greetings everyone, I'm Yuan from the Physics Department of National Zhongxin University, and today we'll report about Single Lens Telescope. The problem is to construct a telescope using only one lens and a pinhole. We will discuss how the structure of the telescope influences of quantity of images, like magnification, sharpness, and brightness. My report includes the following. We simulate the system according to principles of geometric optics and apply the result to construct the telescope and see how the images behave according to our design. Finally, I will make a brief conclusion. The path of each light ray goes through the lens that is resolved from the diffusive reflection on the surface of the object is calculated using the ray transformation matrix, which is listed here. And the path of each light ray goes through the lens that is resolved from the diffuse reflection. We consider two light sources, green and red, with red above green, placed with the same horizontal position to examine the resulting image. The relevant structural parameters are the focal length of the lens and the radius of the pinhole are 19.25 centimeters and 0.2 millimeters respectively, and coordinates of the source are 0, 2, and 0, -2. Here's the simulation result with the distance of the pinhole and the lens are 12 centimeters and 50 centimeters. Both are within the focal length. It is clear that most of the ray paths through the lens are filtered out by the pinhole. We see the resulting image is inverted. Larger distance gives a larger angular separation of the ray, thus gives a greater magnification. When the pinhole is placed outside the focal length, namely 25 centimeters and 30 centimeters, the resulting image is again inverted about but shorter distance between the pinhole and lens give larger angular separation, and therefore a greater magnification. In order to have a clear view, we draw only a few light rays. If there is no pinhole, we see the image should be inverted, but the resulting ray diverges, so that we get a blurred image. With pinhole, we see the distribution of the resulting rays are much restricted, so that the image should be sharp. Here's the visual image with and without the pinhole. The one with pinhole is obviously sharper than the one without. However, the one with pinhole is darker. This is because pinhole allows less light to go through. And this is the sharpness of the previous two images recorded by the tracker. And here we make a short conclusion. The pinhole makes a sharper but darker image. We simulate the light path with 3 different pinhole sites. We see that the resulting red diverges more as the pinhole gets large. Because larger pinhole filter less red, however, more light will make a bright image. And this is the actual visual image created by 3 different sizes of pinhole. Obviously, the image with larger pinhole is brighter. And here we see again the brightness increases as the pinhole gets larger. And to enhance the contrast, we compare the images of the smallest and the largest pinhole. It's clear increasing the pinhole size makes the brighter above blurry image. And make a short conclusion. Larger pinhole creates brighter but blurry image. And conclusion. The effect of the pinhole is to filter out light rays of specific directions. Smaller pinholes produce sharper but darker image, and the larger pinhole creates brighter but blurred image. Numerical simulations show that when the position of the pinhole is closer to the focal point of the lens, and the magnification gets greater. And thank you for attention.
Thank you for the report. So now we have 2 minutes for all the teams to prepare the short questions. Okay, so now it's time for Team C to ask Team A and Team B the question. So, Team C. Please.
I want to ask Team C and Team B. What is your difference of Team D and R?
Ask me.
Yeah.
D is the diameter of the pinhole, but R is the diffraction dot on the retina. We review it's the iris, the radius of iris.
Thank you.
Any other question? now it's time for Team B to ask both Team A and Team C questions.
Okay. Firstly,
To Team A, that do you think the magnification is no matter with the length of your telescope or the location of your pinhole?
Yes, it does. You can see my formula here. Here, this L is the distance.
Okay, I know. And then, do you think the magnification will influence the illuminance of the image?
First, I think we have different definition for brightness, but yeah, it does. It's also here.
okay, I know.
And for both A and C, I'd like to ask you that, hey, both of you, I'd like to ask that, is there any probability to make the telescope with a concave lens? That we all of us make it with a convex lens, right? Yeah. Is there any probability?
Well, I don't think so, because usually the telescope, the objective lens usually is a convex lens. It's not a convex.
Okay, I know. And to you, could you describe how did you NTF your experiment result?
Oh, you mean how do I get the MTF?
Yeah.
I don't think I added on the aperture, but there is some simple explanation for that. Here, MTF is widely used, and this is partly of this one, partly of the quality we have is from the textbooks. No, it's from a reference, but there are part of it from the reference, and another part is from our telescope. Because on the reference it's about a real telescope with two lenses, and all I did was change it to the eyepiece with the aperture. So
Okay. Thank you. And do you think the grade level could maybe replace the naked eye? Because the maximum of grade level is 255, right?
55 units?
What?
Units?
No. It is a parameter on your computer screen.
Oh, I see.
Okay.
So what's our problem there?
Do you? Because our eyes have no maximum for the brightness, right?
No, it has.
Okay, it has, but really high. Yeah, we could find the brighter, really brighter, and really darker. But on your camera, do you think the?
Yeah, that's why we gave up the brightness and used modulation transfer function.
And the last problem, how did you use tracker in your experiment? I think tracker is
Okay, time is up. Now it's time for Team A to ask both Team B and Team C questions.
Oh, well, I think we should let lady first. So, Team C. So I see that you use Python to simulate the light, right? Can you further explain like what is the axis of your picture? Because I'm not pretty sure what that means. I'll go to that later. You can put that on. First, I will ask Team B. Please just go on. So it's on page 7. So Team B. So I see that the magnification. You consider when L is smaller than F and L is larger than F, right? When it's in front of the image and back to the image. What would happen if L equals to F?
When L equals to F, we could see in the hyperproduct that the hyperproduct goes to infinite, and there is no image.
I know that's your theory, but what would happen for your experiment?
Just like when you use a convex lens to a sample, it's just on its focus, and you say that it's really blurry and nothing.
Okay, thank you. Okay, Team C. Can you explain the axis of the picture? What does that mean? The distance. This is the distance.
Yes, before
And
our
this.
convex lens here and our object here.
So and this is the ray.
Yes, and it's below.
Okay, thank you. And for Team B, so how do you get your grade level image?
By PS.
Okay, Photoshop, I see. And can I see your definition of sharpness again?
It is the gradient level, gradient of gradient.
The gradient of the grade level. But what would happen if the intensity changes? When the intensity gets higher, would the gradient get higher?
What? Okay, your sample really changes the grade level, because if you use a sample is purely black, maybe you have no grade level, of course.
And another one is when you said there is a Fraunhofer diffraction, right?
Yeah.
Can you turn to that page? The iris disk you have. You have
The
simulated.
simulation run. I will find it.
Okay. So for Fraunhofer diffraction, it needs to have far field condition. Yeah. Do you have far field condition for this one?
Our sample is really far. Secondly, the diffraction is really on our retina. You know, retina is a focus plan of a convex.
I see. But if it's too far, you cannot see any image because it's too dark, right?
It is far, is no matter with it is far.
But there's an aperture, so the intensity of light is very low.
No,
No?
we have the really
Okay.
far sample. You could say.
Okay.
So
Thank you.
time is up. So it's time for all three teams to prepare for your discussion, and you have 2 minutes. Alright, the preparation time is up. So it's time for all three teams to discuss the differences or any other important issues. So anyone would like to start? But please, all three teams, so come to stage and so anyone would like to start?
I think we should let Team C start. Yeah.
Okay, so then Team C.
Because they did first, right?
Anything you wish to discuss?
I want to ask Team A. How did you measure your magnification?
Magnification?
Yes.
The definition of magnification is the tangent, the ratio of tangent, right? So we measure the size of the image or the object and the distance between the object and our eyes. So we can calculate the tangent and then we can calculate magnification.
The size of the image?
Yeah, the length of the image. Yeah, it's here. You see, we calculate y, and the distance between the object and our eyes to calculate the tangent.
And I want to ask your error analysis about brightness.
Brightness, right?
The camera decision in camera and the kitchen eye. And difference in camera and the human eyes. And what's your brightness error analysis?
Okay. Here. You see, when we take photos with camera, camera can fit adjust itself to the environment. And these two images both came from the same camera to take the same image, but you can get this different sharpness, right? Because the photo is different, so there are pretty much a big error. So we gave up sharpness and we used our modulation transfer function to replace the sharpness.
And I want to answer and as your illuminateness proportional to this graph, and it only have 5 data points. How can you show your fading line is correct?
They like PowerPoint. And this is not a fitting line, but it's not a fitting line, but it's a series line. So the 5 points couldn't draw a line, but the right line is a series line, but the dots are the experiment dots. I have to. Firstly, to Team C that what do you think the effect of the pinhole?
Team A.
Oh, Team A. I'm sorry. What do you think the effect of the pinhole?
The effect of the pinhole?
Yeah.
Yeah, it affect the it affect the brightness, and we see that here, and the clearance. We don't use sharpness, we use modulation transfer function.
Yeah, you mean the pinhole makes it sharper?
You can see that, but we don't use sharper. We use clear.
Okay. And the second question that why doesn't M influences the brightness of image?
You see, it does.
You think it does, and in this point we have different. We have a difference. Yeah.
Okay.
So I'd like to see your PPT again.
Sure.
But for your record, I want to remind you that we have a different definition of brightness. You use illuminance, but I use luminance. So the question is, if the image size is smaller, the energy is conserved, right? So I think it can get brighter because the image is smaller. If it gets to a point that must contain large energy, so I think that contains it's brighter than if the image is larger.
Okay.
So it does influence the brightness.
That's just a definition difference.
No, if you use illuminance, I mean, if you're so the magnification doesn't change the brightness, right?
Right.
But it does. I mean, for our instinct, if the object, the image is very small, it's brighter, and if it's large, it's darker, right?
However, the light line goes into the telescope at the same.
So you think if the size of the image doesn't change the brightness?
Yeah.
So, but how does the energy would conserve? The energy doesn't conserve, right? If it's larger and it's same brightness as it's smaller, it must contain larger energy.
I think your maybe you are based on the traditional telescope like this, and it's that's right. And you think this area is proportional to d squared, right? M squared. I'm sorry. Yeah. But we use another one. That is it is not parallel. It is like this. Maybe I different.
Well, you see, this is our experiment. The figure 1 and figure 3 have a different magnification. And you can see, do you think these two have the same brightness?
But in our experiment, do you think this is? Sorry.
Can I ask a question first?
Okay.
So, is there any general conclusion, like what would the three factors, magnification, sharpness, and brightness, as a whole, affect the image? I mean, I see that your series separately. Is there any mixation of how does these three together affect the influence the image?
I think these are three separated parameters. But I think you define it as the sharpness of the brightness and that is. But I think it could show something, but it is what you define. If I am interested in the brightness, I like to make my image brighter and brighter.
Well, I think you should ask Team Caesar first because you keep asking me.
Okay. Oh. No. I have prepared it. Oh, I'm sorry. It's this.
I'll go first. So, you see, if you use Photoshop to get the grid level, there are many methods and different grid level image. So here, there are at least 4 methods to get grid level. And this one is just the average of the pixel of red, green, and blue.
And another, this considers the sensitivity of our eyes to the different wavelengths. Like human eyes are more sensitivity to gray light, so it's different. You can get different gray level, and then you can get different brightness, sharpness, right? So do you know how do you get gray level?
Oh, I'm sorry. I beg your pardon.
Okay. So how do you get your gray level? Because you use Photoshop, right?
Yeah.
So there are different methods to get gray level. I mean, this is just average of the pixels of the red G and B, and this is considered the like the sensitivity of human eyes, because human eyes have more sensitivity to gray light.
Yeah.
So you know how you get that?
I got it just like this, and its maximum is just
Which one?
25.
At least there are 4 or 5 methods to get different gray level.
The average of the RGB turn-on. Yeah.
Okay.
And if you will, you'd like to have an image on your retina, what does it mean? Just use the function that the intensity of your eyes.
And I have a question for both teams. So, do you have ever considered how to make a best telescope? I mean, you have already considered all of these parameters. How will influence the factors? Is there a best telescope?
I think it's not best telescope because everyone is not interested in the same parameter.
Well, but I think everyone is interested to have a better performance of the telescope, right?
Yeah.
And Team C?
Yes.
Do you have any consideration on that?
I could finally show our experiment result that you could find that it is the maximum, the magnification is 20, and this magnification is only maybe 10. As the proportional to m squared, it could be 1 out of 4 bright. Yeah, but it looks the same bright.
But you are using camera to take photos.
Yeah.
That will change brightness.
No.
Won't
Not the phone camera, but
you see?
yeah, the same.
Sorry, the time is up. Now, all 3 teams have 3 minutes to prepare your conclusion. time for Team C to make your concluding statement. You have 2 minutes, please. Please be louder and take the microphone. Okay, so please go ahead.
Team A and Team B both give a clear definition of sharpness and magnification, and Team B have quantity of the best counterpart of the best telescope, and we don't do that, but we do many simulation and make more clear in magnification. Thank you.
Thank you. So now it's time for Team B to make your concluding remarks. Please take the microphone. So please go ahead. Okay.
Hello everyone. Firstly, both the Team A and Team C has many advantages that they're all clear and easy to understand. And Team A use modulation transfer function to analyze the modulation degree, and Team C explain the use of pinhole clearly and use Python to simulate. And in our discussion, we asked many questions, and we found what I to say again is we have studied the distortion of the image. This is the palo distortion and the barrel distortion and the others and aberration. And the next one. In our conclusions, I'd like to say again that in our experiment, we didn't find the magnification and influences the brightness. And another thing is that we used the CCD camera in our experiment and with the same aperture. That means the CCD couldn't maybe be brighter or be darker by itself. Yeah, of course. And we found that F and L influences magnification, and all these three parameters influences the sharpness, and only diameter of the pinhole influences the brightness. Yeah, that's all. Thank you.
So, thank you. So now for Team A to make your conclusion.
Okay. So for Team B, the advantage is that they have directly seen the difference between images with different devices. I see a lot of figures, a lot of images, and the lens. And their conclusions are shown clearly with quite clear conclusion and summary. And but the disadvantage is that there is no explanation on how sharpness would change. I mean, the sharpness of how the sharpness change with the brightness will change, where it influenced the sharpness. And another thing is that I didn't see your page number, so it's hard for me to ask you questions. Okay. And for Team C, the advantage is that the whole description is concise and the simulation about lights are vivid. I really like your simulation really with programming Python. Actually, I've done the same thing. And here's some advice if you want to take that. You can consider many other things like the thickness of the lens. Because you are using Python, it's pretty easy to do that. And the aberration, like this is what I have done with simulation here. The aberrations, and consider the thickness and the aberration of all kinds of like spherical, but I gave up that because I don't know the theory of aberrations. And we have already got the modulation transfer function for the quality, so we gave up that. And the disadvantage is that there is no parameters about diagram, and didn't investigate all the paragraphs. And I want to make a summary about the discussion because we have different definition of brightness with Team A and me and Team B. And we get that camera, we can use a better camera to get the photo. That's true because using iPhone is not the best choice. Yeah, that's all. Thank you.
Please, three teams to go on stage. It's time for the jurors to ask questions. Any questions from the juror members? Questions?
So I will ask a question starting from Team A.
Okay.
How do you think this single lens telescope is different from an ordinary telescope?
Well, first, the brightness. I mean, you use an aperture, so it must be darker than the telescope we use. And another thing is about the magnification. Because we only have one telescope and one aperture. The magnification performance of the aperture is clearly not as good as another eyepiece. And the other thing is that it's influenced by the modulation transfer function. I mean, you won't get as the quality of the both two lens telescope because we are using aperture, and I'm pretty sure it gets fuzzier image for single lens telescope. And I think that's all I have considered. Okay, thank you. Do you want to ask Team B?
Yeah. The same question for you.
Okay, I think in the real telescope, it is maybe it makes an image. It makes a real image that is like this, on the infinite way. Yeah, from a sample from infinite makes an image from of infinite. But in our telescope, a sample from infinite makes an image on just in front of your eyes, and this is much blurred because it's too it's too near to your eyes, and you must use an aperture. Yeah.
Okay, you answered the same questions.
I think single lens telescope in control the brightness is very weak.
Okay, right. So I also have a question not for Team B. So you kept asking other teams about what happens if you replace the convex lens by a concave lens, right? So what's your answer for that?
Yeah. For me, my opinion is just say to the team A that a concave lens cannot make a real image. So it couldn't make a telescope. Yeah.
Any questions from the juror?
I have two questions. The first is, can you do three things? Can you explain the pinhole, the separate and the defect?
Excuse me? Could you please
Separate.
Separate.
Yeah.
The pinhole separately? Only
And
the
the
pinhole,
defect?
right? Or
Only pinhole?
just the influence of the pinhole, right? Oh, okay.
Where is the microphone?
Well, first the pinhole. Firstly, the pinhole is act like a diaphragm. That is just the one we use on our cameras, the aperture. So it can flit light, so make the image more clearly with a sharper edge. Another thing is that it can get, it could change the magnification, like a pinhole camera. It can also function like a pinhole camera to magnify the image. And it will also influence the clearance of our, as I said, the quality of the image, because if it's a small hole, so it can, the diffraction is pretty obvious for a pinhole, so it will also change the quality of the image.
Okay, for me, because the image is really near to your eyes, you must use a pinhole to decrease the angle between the light lens and the axis. Therefore, you can get a clearer image. And did you ask for the single pinhole? Okay. For a pinhole separately, you could get an image like this. We all studied in our senior high school, and but the sharpness of the image is limited because there is a diameter of the pinhole, right? Yes.
So again, Team C, please answer the question.
I think the pinhole can fit our light and it can never image is more than but dark.
Sorry, but actually we only have 5 minutes for jury questions, and the time is up. So thank you for all 3 teams. Please sit down, and it's time for jurors to make the scores. All the juror members ready? Yeah. So let's start from the Team A's score. So let's please show the scores for Team A. The scores are 8, 8, 9, and 9. So the scores for Team B. Okay. Please show. The scores are 7, 9, 8, and 8. So now the scores for Team C. The scores are 5, 8, 7, and 7. So, all right. I think I will make a very short comment for 3 teams. So first to Team C. So first to Team C. So although in compared to the other 2 teams, your results are less or fewer, but I think you can still take more of your time to explain what you do, especially for the simulation, more clear, and then you will give us a better whole idea of what you learn. So that will make that could make us more understand more about what you did. Okay. And more into some physics, so what you did. And also a very short comment to Team A. So you did a lot of great works, especially from the theory part, but I think one thing you could do more and then make it better is that after you explain all these theories and not only say the formula like this, but just state that which parameters in your experiment and what is the trend? For example, if the distance increase, how that will change, and then we will get a clear image in your experiment results. Okay. So any other comments from the juror members? No. And then I think it's a great fight, and thanks all 3 teams, and thank all the juror members. So this is our conclusion of the fight. Thank you very much.